morning everyone, welcome back to your physics class once again. You remember that last time we started the chapter calorimetry. In calorimetry we discussed about heat. I hope you all are remembering that heat is the energy in transit, that a body possesses some internal energy, thermal energy, and then two different bodies having two different internal energies, and when they come together or when we bring them closer means in contact with each other, then the energy flows from one body to the other body, and that energy in transit is known as heat. This I think we have discussed. And then also we discussed the temperature. We discussed what is temperature and how can we measure temperature. We discussed the definitions of temperature, like it is the degree of hotness and coldness, that we have learned in junior classes. Also we have seen that temperature is a parameter which decides the direction of flow of heat. Means if you have two bodies and you have the bodies are on two different temperatures, you can always tell the direction of flow of heat by knowing their temperature. Also we were seeing that if we want to raise the temperature of a body, like if I'm having a body and we want to increase the temperature of the body, we have to give the amount of heat. That means the body will absorb heat and its temperature will increase. So this we have discussed, and I want to revise that a little bit, that if let's say we are denoting heat by Q. Okay, now if a body is absorbing Q amount of heat, then to raise its temperature, so this amount of heat absorbed by the body depends on the mass of the body. That means amount of heat absorbed will be directly proportional to the mass of the body. Means this we have seen in the last time, that more mass, more heat will be required to raise its temperature. Also the heat absorbed is directly proportional to the change in temperature required. If you want to change the temperature of the body by 1 degree Celsius, you have to give some amount of heat. But if you want to raise the temperature by 2 degrees Celsius, that means now more difference you want in temperature, that means you have to give more heat. This we have seen. And what we did is that we are having this two expression and we combined the two expression. We combined it and we got this Q directly proportional to m into delta T. This we have seen. Also when we remove the proportionality sign, we always use a constant, that is known as the constant of proportionality. So Q equals m. Here which constant we are using? C, and m and delta T. Here if I write it properly, it is m C delta T. Here this C, which is the constant of proportionality, the name given to it is specific heat capacity. I think this we have seen, specific heat capacity. Now till here we have seen. Now let's see a little more, that if we want to calculate this C, this m and delta T will go to that side. That means Q over m into delta T, and this is equals to small c. Now that small c is specific heat capacity. Now let us define this specific heat capacity. It is, if you read the definition, because now we are having another term. This one is specific heat capacity. We have another term, heat capacity, and you should know the difference. Now this one is specific heat capacity, and if you want to define, it is the specific heat capacity is the heat, it is the amount of heat absorbed by 1 unit mass of a body. Unit mass of a body. Unit mass means it could be 1 gram, 1 kilogram. That means you need to take unit mass of a body to raise its temperature by 1 degree Celsius. Simple. That if you define, it is the heat required by a substance, or it is the amount of heat required by a substance to increase its temperature by 1 degree Celsius of a unit mass of the substance. That means what amount we are taking? Unit mass, and we want to increase the temperature. Like if we are taking a unit mass of a substance, unit mass means it could be 1 gram, it could be 1 kilogram, anything, it could be 1 mole. So if you are taking a unit mass and you are giving some amount of heat to raise the temperature, let's say the body is at 14 degrees Celsius and we want to raise the temperature up to 15 degrees Celsius. That means the change in temperature will be 1 degree Celsius. That means we are raising the temperature by 1 degree Celsius, and then the amount of heat required is known as the specific heat capacity. Okay, so here, and I think last time we have seen the unit, it is joule per kilogram Kelvin. Okay, this unit we have seen, the specific heat capacity. Okay, now since this specific heat capacity is constant, that means the value is not changing, but it is different for different substance. Like specific heat capacity for ice is different, for water it is different, for copper it is different, for different substances or material the specific heat capacity will be different. Okay, also if you are taking this unit mass, if you are taking the unit mass as 1 mole, see, amount of substance you can take 1 gram, 1 kilogram, you can take 1 mole. If you take the amount of substance as 1 mole, then this specific heat capacity will be known as molar specific heat capacity or molar specific heat. Okay, so this is there. Now we have another term, that is heat capacity. Here I have written the definition so you can see properly. Specific heat capacity, which we denote by small c. Okay, amount of energy required, amount of energy of course Q required to change the temperature, that means delta T, of unit mass, means whatever substance we are taking the unit mass of the substance and to change the temperature by 1 degree Celsius, that means 14 to 15 or 30 to 31, that means we are changing the temperature by 1 degree Celsius. And you know what to remember is that the definition by we have to change the temperature by 1 degree Celsius, and you are taking the unit mass, and then the amount of energy required is known as the specific heat capacity, denoted by small c. Now the next term is heat capacity. It is specific heat capacity and the other one is heat capacity. Here if you see, we are changing the temperature by 1 degree Celsius and the amount of heat required. And in heat capacity, we will change the temperature by 1 degree Celsius and we will be calculating the heat required, but we will not take the unit mass. Instead, we will take the whole body. We'll talk about the whole body. That means if we talk about the heat capacity, it would be the energy required for a body or of a body to change its temperature by 1 degree Celsius. That means this time for heat capacity we are taking the whole body. That means we are talking about to change the temperature by 1 degree Celsius of the whole body. So that is heat capacity. Now heat capacity means it is same, the definition is somehow same, that it is the energy required to change the temperature of a body, and then it is the energy required to change the temperature of the unit mass of the body by 1 degree Celsius. I hope, and then you know the definition. And by the way, according to the definition, specific heat was this: Q is equals to mc delta T, and then C is Q upon m into delta T. Whereas if you talk about heat capacity, it is the ratio. In fact, is heat capacity you denote by capital C dash. In your book it is given capital C dash. It is heat required, whatever amount of heat required, and then rise in temperature. Rise in temperature. This is the definition of heat capacity. Now you need to be very clear, or very you should have the idea that specific heat capacity we denote by small. Whenever you see small c written, it is specific heat capacity. Whenever you see C dash, capital C dash written, it is heat capacity. Okay, and small c is Q upon m into delta T, or simply Q is equals to mc delta T. Whereas capital C is heat required. It is the ratio of heat required and rise in temperature. Now heat required, how do we denote heat? So C dash would be heat required, means Q amount of heat required upon rise in temperature. How much temperature rise or how much change in temperature is there. So change in temperature, how we show? We will show it by Q upon delta T. Now if I ask you to write the unit for heat capacity, you can simply write it by seeing the definition. Unit of capital C would be Q is heat. Heat would be, we will measure in joule per. This is delta T. Delta T is your temperature, so it should be in Kelvin. So joule per Kelvin. Somewhere you can also see joule per degree Celsius, but this is more preferable, joule per Kelvin. So now we have heat capacity and this specific heat capacity. Okay, now we know that the heat capacity C dash is Q upon delta T. And how do we know specific heat capacity? It is Q is equals to mc delta T, or simply small c, which is specific heat capacity, is Q upon m into delta T. Clear? Now if you see, we have this Q upon delta T. Can you see Q upon delta T? This Q upon delta T is nothing but heat capacity. So it is C. Q upon delta T is heat capacity upon M, or you can bring M this side. This will simply be C dash equals to M into C. Now that means heat capacity, C dash is what? Heat capacity is equal to mass into specific heat capacity. This is small c. This is very important thing, that the relation between heat capacity and specific heat capacity is equals to m times specific heat capacity. This is important and this will be used in numericals also. Okay, now let's discuss this heat capacity a little more. Okay, what we have learned by definition, that specific heat capacity of a substance is the amount of heat required to change the temperature of a unit mass of a body by 1 degree Celsius. We are changing the temperature. That means this is the amount of heat required. More heat you are giving, so you will get more specific heat. That means if you have high specific heat, this means that you have to give more heat, or the substance will have more heat. I am just telling you the relation, isn't it? Are you able to relate? Now that means the vice versa condition. That means if you are having low specific heat, that means less heat, isn't it? Correct? That means if you are taking two substances in which one is having high specific heat, the value of specific heat is high, and for one the value of specific heat is low. So in that case, the one which is having high specific heat will be absorbing more heat, like to raise the temperature of the body by 1 degree Celsius. Now let's see, if I am having a body A and I am having a body B. Okay, now let's see, for this body the specific heat is, let's say 39, whatever is the unit, joule per Kelvin kilogram, and this, for this one, let's say it is 390. So that means the specific heat of B is greater than the specific heat of A. That means for this one, if the value of C is high, that means it will absorb more heat. Now let's say that both the bodies are on same temperature. Same temperature means A is at 10 degrees Celsius, B is also at 10 degrees Celsius. I hope you are getting the situation. We are taking two substances, two bodies, both at the same temperature but with the different specific heat, the value of different specific heat. Now according to the definition, we have to increase the temperature by 1 degree Celsius. That means we have to make the temperature of both the bodies 11 degrees Celsius separately. We have to give this body some heat, we have to give this body some heat, and then I am asking you to increase the temperature by 1 degree Celsius. Who will absorb, or which body will absorb more heat? Of course, more heat will be absorbed by the body which is having high specific heat. That means this body B will absorb more heat. Likewise, if you take the example of copper and water, okay, you are aware of copper and water. In case of copper and water, copper will have less specific heat in comparison of water. That means water is having high specific heat. Now let us understand the meaning. Water is having high specific heat means, if it is having high specific heat, that means it will absorb more heat to increase its temperature by 1 degree Celsius, whereas copper having less specific heat will absorb less heat to raise its temperature by 1 degree Celsius. Clear? Here we have taken two vessels having the same amount of water and copper. That means the mass in both the vessels, water and copper, they are same. M is same. Okay. And we want to, like if it is 1 kg, this is also 1 kg we have taken. And if you want to increase the temperature of copper and water both by 1 degree Celsius, so we have to give some amount of heat. Now, if we are giving some amount of heat, which one will take more heat? Water. Why? Because it is having its specific heat capacity 4200 joule per kilogram Kelvin, whereas this one is having its specific heat capacity 399 joule per kilogram Kelvin. That means this will take more heat to increase its temperature by 1 degree Celsius, and this will take less heat. By the way, if we are having two bodies, this is taking more heat, this is taking less heat. So that means if we are, let's say it is at 10 degrees Celsius and we are giving heat to this one, and when we give heat, it will quickly increase its temperature because it will absorb less heat. Whereas this one will take time to increase its temperature, isn't it? Because it will absorb more heat. And if it is taking time to increase its temperature, that means it is absorbing more heat, or it is storing heat into itself. And that's how all those substances which are having more specific heat are supposed to be called, or are called, heat reservoirs. Reservoirs. The substances which store heat in itself, because it will be taking heat continuously but it will not be increasing its temperature by 1 degree Celsius. Why? Because it is having more specific heat. This is the quality, or this is the property of a substance. It is a characteristic property of the substance. I hope you are getting the idea. Whereas if this one is having less specific heat, that means it will absorb heat and it will quickly increase its temperature by 1 degree Celsius. So it is easy to increase the temperature of copper rather than increasing the temperature of water. Water will absorb more heat. I hope, and this is given in your book. If you read the article once or twice, I think couple of times, you will get it, you will understand. And but then once you get it, you will see that there are many substances which are known as heat reservoirs. You can also search on the internet what is heat reservoirs. There are many substances. When you will go to class 11th, you will study about this refrigerator, you will study about the heat engines, and there we use the term in thermodynamics, heat reservoirs. And these are, they are the pool of energy. How they are the pool of energy? Because they are absorbing heat into their cells and they are not increasing the temperature. That means they will take as much heat. That depends on their substance and the quality of substance. They will absorb heat and they will not show any change in temperature quickly. Of course, the temperature will increase, but not very quickly. And this is about the specific heat capacity and the heat capacity. And I am expecting that you all can differentiate now between heat capacity and specific heat capacity. Now let's further move on. As we have learned that to measure temperature, we can measure temperature, and which apparatus is used to measure temperature? Thermometer. Likewise, we discussed that heat flows from a body at higher temperature to a body at lower temperature. That means heat is also a measurable quantity. We can measure heat, and the apparatus which measure heat is calorimeter, we have learned, and this process is known as calorimetry. Okay, so this is what we are studying in our chapter calorimetry. We are all focused on the measurement of heat, how it is flowing from one body to the other body, what amount of heat a body is absorbing, what amount of heat a body is releasing. Because what we study, if we are having two bodies at different temperature, let's say body A and body B. Body A is at 10 degrees Celsius, body B is at 40 degrees Celsius. So heat will flow from body B to body A. We know that. And since heat is flowing, let's say 10 joule heat is flowing from B to A. First question, that means this is the measurable amount. We can measure heat by using calorimeter. Second is that we are deciding the direction because of the temperature difference through which we can decide the heat will flow from which body to which body. Now let's see how this calorimeter works, or how can we measure this amount of heat using calorimeter. By the way, if you're having two bodies in contact and we have taken two bodies A and B, in which one body will gain energy or heat and the other body will lose the energy or will lose the heat. Is it clear that if two bodies we bring in contact, one body will gain and one body will lose? This is the idea. So here we are having calorimeter, how it is working. What is there? We are having, we take a copper vessel, simple, a copper. Why we are taking copper vessel? Because it is having low specific heat. Low specific heat means a less amount of heat required to change the temperature. If we take any liquid, say water, in the copper vessel, so copper vessel will can be heated easily because it is having low specific heat. And then we take whatever substance we want to take, water, whatever, sugar solution, whichever value we want to take, and then we have this two hole. One hole we put a rod which can stir to mix the content, or to when you are stirring it, that means you can easily cool it down also. And one is for the thermometer, that means in one we are using the stirrer, one we are using the thermometer. You can put any solution if you want, or you can put water, whichever subject or whichever object you want to check. Okay, and this one is made up of copper. And then we put this system. What is the idea? We are going to measure the heat. If we are giving a substance some amount of heat, we want to measure the amount of heat, simple, calorimeter. So now after that we put it in a wooden box. This is a cover, we put it in a wooden box. Why are we putting this system into a wooden box? So that if we want to measure the heat, some amount of heat should not be lost in surrounding, because we know that heat can be radiated or it can be conducted into the surroundings. So to secure it from that, we are putting it into the wooden box, so that to make it isolated from the surrounding. Okay, also we this wooden box and this copper box, between this we put some cotton, or we can put whatever, some bad conductor of heat. You can leave it like that also, because air is also bad conductor of heat. And then we place this thing, a lid, so that it is all isolated, it is from the surrounding, so that no heat loss should be there. The calorimeter, the procedure is written in a book. By the way, I am going to tell you that the experiment which I have performed in my college days is that we were given the calorimeter, and we were supposed to calculate, we were supposed to check the idea that if we are having a body A and we are having a body B, A is at 10 degrees Celsius, B is at 40 degrees Celsius, and if we are bringing them closer in contact, of course heat will flow from body A to body B. Means this body A will gain heat and this body B will lose some heat, or there will be heat lost, isn't it? I'm going to tell you how I did this in my college. Okay, now this one is a copper vessel and this one is a wooden box. Okay, now what we did is that we took some water and we heated that water. Okay, that means if you are heating that water, you are giving some amount of energy to it. That means you are giving some amount of energy, it is gaining some energy. Let's say you are giving 70 joule amount of energy to this water and you are heating it up. Say initially the water temperature was at 30 degree Celsius, and when you are giving 70 joule, let's say it become 40 degree Celsius. That means you have increased the temperature by 10 degree Celsius and you are giving 70 joule amount of heat. So you will measure this temperature change by thermometer. Clear? Now if you are giving the heat, that means this water is gaining some heat. After some time, after this, if we cool it down, we cool it down again from 40 degrees Celsius to 30 degrees Celsius. Okay, cooling it down. So what amount of energy should be released from this water? Of course it should be released, it should release 70 joule, because whatever amount of energy should be gained in increasing the temperature, it should be released also when we are decreasing the temperature by the same amount, isn't it? In the ideal condition, or in the condition when there is no loss of heat, no loss of heat in the surrounding. I hope you are getting it. That means if we have isolated, if we have somehow able to properly isolate it from the surrounding, this system should be performing well. That means whatever amount of heat gained by a body, heat gain should be equal to heat loss. Okay, but in that case the system should be isolated, because if the system is not, it is having in the surrounding, open surrounding, then it will not work. That means this system will not work. So this is the condition when you are having heat gain equals to heat loss. This is the actually principle of calorimetry, and then how you can measure. By the way, even when you do this and when you use this calorimeter, you will see that there will be some heat loss. There will be some heat loss. That means the amount of heat gained by the body will not be equal to the amount of heat lost by the body. This is the thing, because some of the energy, because this wooden jacket which we are using is not able to control the heat. The heat will be lost in surrounding by radiation or by conduction or by any means. By the way, if in the ideal case, or if we can easily isolate properly, then it should be there that heat gain should be equal to heat loss. And this is the idea, or this is the principle of calorimeter. This is also known as principle of calorimeter. It is also known as principle of mixture. There is a question in your book, you can see it is the principle of mixture. Heat gain should be equal to heat loss. And from next on, there are many questions based on this idea that heat gain should always be equal to heat loss, unless there is no exposure of the body to the surrounding. If we are having the body perfectly isolated from the surrounding, we can say that the heat gain should be equal to heat loss. Principle of calorimetry or principle of mixture also. Okay, now see the mathematical expression. To see the mathematical expression, let's take two bodies, body A and body B. Okay, now the mass of body A is MA, the mass of body B is MB. Okay, let's say the temperature of body A is, you can take it as T1 or you can simply take it as TA. The temperature of body B is as TB, and you can say that the temperature of body A is greater than the temperature of body B. In some books the temperature can be shown by theta, so no problem, it is just the notation. Okay, so here we have, and since the body A is at high temperature and body B is at low temperature, that means if we bring them closer, bring them in contact, the heat will flow from body A to body B, correct? That means heat lost by body A, because heat is flowing from A to B, should be equal to heat gained by body B. Is it correct? This is the principle of calorimetry. Now also go back to the thing which we have learned, that the heat lost or heat absorbed by the body, what is the formula? The formula was Q equals to mc delta T, isn't it? This we have learned. So we are going to apply this. Heat loss, what amount of heat should be there? mc delta T, and same will be equal to heat gain. Now mc delta T, and by the way, if the body A, let's say the specific heat for body A is Ca and specific heat capacity for body B is Cb. So according to the formula, it should be mc delta T. M is Ma, C is Ca. Okay, now according to the formula, it is mc delta T. Delta T is what? The difference in temperature. If we have 40 degrees Celsius and 30 degrees Celsius, what will be the temperature difference? 40 minus 30, that means higher minus low, that is the difference. So here, if we are talking about body A, TA will be greater, T will be smaller. So what will be the difference? It should be TA minus T, isn't it? This is delta T equals to heat gain. Heat, which one is gaining heat? This one. So mc delta T, what is M here? MB. What is specific heat? Cb. Delta T, change in temperature. Now what is change in temperature? That is higher minus lower, that is T minus TB. This you can simply apply. It is simply MC. You are going to apply this formula MC delta T, that is mass, specific heat and change in temperature. And this is the idea of principle of calorimeter, that is heat lost equal to heat gain. And this is the mathematical expression. Now keeping this all in our mind, let us simplify the numericals. Here I am going to take very first question. It is page number 270. I'm going to solve the question first, numerical. Now, by imparting heat to a body, its temperature rises by 15 degrees Celsius. There is a body and the other body is imparting heat and the temperature rises by 15. There is a change in temperature by 15 degree Celsius. What is the corresponding rise in temperature on Kelvin scale? You are supposed to tell the corresponding temperature rise in Kelvin scale. By the way, this 15 degrees Celsius is not the exact temperature. It is the rise in temperature. That means change in temperature is given as 15 degree Celsius. And you have to tell or you have to calculate what is change in temperature in Kelvin scale. So if you remember in last class we have learned that the temperature difference is same in both these scales. It is, I think, on page number 262 you can see that change in temperature on degree Celsius scale or Celsius scale is same as the change in temperature in Kelvin scale. So if the temperature change is 15 degrees Celsius in the Celsius scale, it will be same in Kelvin scale as well, 15. Okay. Question number 3. A piece of iron of mass 2 kilogram. Now, piece of iron with mass 2 kilogram given has a heat capacity. It is not specific heat written. It is written heat capacity, and heat capacity is denoted by capital C dash, which is given as 966 joule per Kelvin. By the way, you can read the word, otherwise you can see the unit also. Now find the heat energy needed. You are supposed to calculate heat energy. So we denote heat by Q. Energy needed to warm it by 15 degree Celsius. How much temperature change we want? 15 degree. Whatever was the temperature, 40 degrees Celsius, so we have to change the temperature by 15 degrees Celsius. That means we have to make it from 40 to 55. Okay. And second one is we have to calculate the specific heat capacity, which we denote by small c. This is the question we have. Okay. We know that heat capacity, that is C dash, is m into specific heat capacity, and we have to calculate specific heat capacity and Q also. How to calculate Q? We know the formula for Q is mc delta T. We should know m given, we should know c not given, we should know delta T given, that this one is delta T. That means first we have to calculate the specific heat. How to calculate specific heat? By using this information given. We have already learned that this heat capacity denoted by C dash equals to m into specific heat. So this heat capacity is given as 966, m is given as 2, and this specific heat we want to calculate. Of course, this will come to this side and small c will be 966 divided by 2, or simply 483. What is the unit? Joule per Kelvin kilogram, or joule per kilogram Kelvin. Now since we have calculated small c, this will be the answer for the second part. And how to calculate the first part? We are supposed to calculate Q, energy, heat. That means Q, the formula is simply mc delta T. M is 2 and C is given, we have calculated, it is coming 483. Then we have delta T, rise in change in temperature is 15 degrees Celsius. And when you simplify all this, the answer will come 14490 joule, because this is the amount of heat. Unit we will use is joule. This is it in today's class, and we will be solving more numericals in our next class. And till then, I'm hoping that you all are studying and you all are reading, and this thermodynamics, or you can say this calorimetry, is a very interesting chapter. So I think you should explore this chapter too, and you should read, as I have told you one word, that is reservoir. You should read about reservoir, you should read about heat engines, you should read about how refrigerator works. This is all related to it, and I think you should explore all these things and try to solve numericals, and we will solve the numericals in our next term. Till then, keep studying.